Ever wondered how the heat from a hot cup of coffee diffuses into the room, or how a scent wafts away from its source? These are everyday examples of diffusion phenomena, and to fully understand them, we dive into the realm of mathematics, specifically parabolic equations. Parabolic equations belong to a class of partial differential equations. They play a crucial role in the mathematical analysis of diffusion phenomena, such as the heating of a slab, or the temperature distribution along a thin rod from moment to moment. Imagine a simple one-dimensional scenario. We have a thin rod, and we want to understand the temperature distribution along it over time. Our parabolic equation would look something like this: Ux equals ut. However, solving this problem isn't as straightforward as it might seem. The solutions to this problem, even in its simplest form, are complex. They are constructed largely from a function known as the fundamental solution of the equation, given by an exponential function, xp. But wait, there's more to consider. To determine the complete solution to this type of problem, we must also know the initial temperature distribution along the rod and the manner in which the temperature at the ends of the rod is changing. These additional conditions are known as initial values and boundary values, respectively, and together they are sometimes referred to as auxiliary conditions. Now let's take this a step further. What happens when we move from a one-dimensional problem to a two- or three-dimensional problem? Well, the initial temperature distribution throughout the region must be known, as well as the temperature distribution along the boundary from moment to moment. The differential equation in two dimensions is, in the simplest case, Ux plus Uir equals sine ut, with an additional uz term added for the three-dimensional case. Remember, these equations are only appropriate if the medium is of uniform composition throughout. For problems of non-uniform composition or for some other diffusion-type problems, more complicated equations may come into play. An equation can be written in a simpler form using a different coordinate system and is also parabolic in the given region if it can be so transformed. An equation in one dimension, the higher order terms of which are ox plus buxt plus cut, can be so transformed if B2, 4ac equals 0. If the coefficients a, b, c depend on the values of x, the equation will be parabolic in a region if B2, 4ac equals 0 at each point of the region. To summarize, parabolic equations are a type of partial differential equation that help us understand diffusion phenomena. They require a fundamental solution, initial values and boundary values to solve, and can be applied to both uniform and non-uniform compositions. Remember, the complexity of these equations increases as we move from one to two or three dimensions. So the next time you notice the warmth of your coffee spreading into the room, or catch a whiff of a pleasant scent, remember there's a complex mathematical equation working behind the scenes. The fascinating world of parabolic equations helps us make sense of these everyday phenomena and many more.